Now that we have a little familiarity with chemical reactions, let's look at another chemical reaction. And this time, we are looking at the dissociation of water. What actually happens is this. Two molecules of water react to form a hydronium ion, H3O+, and a hydroxide ion, OH-. Notice how this reaction is balanced, meaning we have the same number and type of atoms on either side of the arrow. 4 hydrogen atoms on the left, 4 hydrogen atoms on the right, 2 oxygen atoms on the left, and 2 oxygen on the right. Okay, this is what actually happens, but we are going to simplify it like this. H2O reacts to form a hydrogen ion, H+, and a hydroxide ion, OH-. And this reaction is reversible. The ions can reassociate to form water. In pure water, the concentration of the hydrogen ions is 1 × 10 to the -7. And the concentration of the hydroxide ions is also 1 × 10 to the -7. So most of the water molecules are still in the form of H2O, but a few of them have split into these ions. And that brings us to the concept of pH. You've probably heard of pH, but what is it exactly? Well, pH is a measure of the concentration of hydrogen ions in a solution. We can calculate pH with this equation. pH equals the negative log of the molar concentration of hydrogen ions in solution. Okay, well, why are we using a logarithm here? In fact, why do we use them at all? The answer is that we want to represent something that can vary drastically in a manageable way. Because pH is going to vary from 0 to 14, and that is going to correspond to a molar concentration of 1 molar hydrogen ions to a molar concentration of 1 × 10 to the -14, or in other words, this number. And that would be really hard to represent in a conventional line graph, so we're going to use a logarithmic scale instead. Here we're graphing pH by hydrogen ion concentration. And now notice that we can show the inverse relationship between these two values in a manageable and linear way. We do this for other numbers that vary super widely as well, not just for pH. For example, the Richter scale to measure earthquakes is also a logarithmic scale where every number represents a tenfold difference. So let's jump right in and calculate pH just as an example. I told you that the concentration of hydrogen ions in pure water is 1 × 10 to the -7 moles per liter, or let's just simplify to 10 to the -7. This is the scientific notation, and if we were to write it out, it would be this. Now I can just use my calculator to take the log of 1 × 10 to the -7, and we get -7, which we multiply by -1 because remember it's the negative log. So that is our pH of pure water. It is 7. Let's do another one just as an example. Let's imagine that the concentration of hydrogen ions in solution is 1 × 10 to the -10th. In other words, this. By the way, is that more or less hydrogen ions than our 1 × 10 to the -7th? It's a lot less, right? In fact, it's 1,000 times fewer hydrogen ions. Okay, same process. Let's take the negative log of 1 × 10 to the -10th, and we get 10. Notice how in each case, the pH was the negative of the exponent? Okay, let's introduce one more concept real quick. The equilibrium constant of the dissociation of water is 1 × 10 to the -14th. What that means is the concentration of hydrogen ions times the concentration of the hydroxide ions must equal 1 × 10 to the -14th. And what that also means is that if we know the concentration of hydroxide ions in solution, we can also figure out the concentration of hydrogen ions because this is an inverse relationship, and then calculate the pH. Here's a really quick example. Let's say that the concentration of hydroxide ions in a particular solution is 1 × 10 to the -8. What is the pH? First, let's solve for the concentration of hydrogen ions. We'll rearrange this equation by dividing both sides by the concentration of hydroxide ions. So that the concentration of H+ equals 1 × 10 to the -14th divided by the concentration of OH-. And then we crunch the numbers and we get 1 × 10 to the -6. Now we can take the negative log and we get a pH of 6. Let's notice two things. First, the pH equals the negative value of the exponent, if we have a 1 here. Second, let's put these concentrations back into this equation and notice that -8 and -6 add up to -14. This is going to be true over the whole pH scale. So, if we have a hydrogen ion concentration of 1 × 10 to the -2, then the hydroxide ion concentration needs to be 1 × 10 to the -12. Notice again that -2 and -12 add up to -14. Now, I wanted to show you how we do these calculations, only so that you understand the relationship between pH, hydrogen ion concentration, and hydroxide ion concentration. Now, we're going to summarize the whole concept that we just went over qualitatively, which is definitely the takeaway message here. It's not the details of calculation. Okay, as hydrogen ion concentration increases, pH decreases, and hydroxide ion concentration decreases. As hydrogen ion concentration decreases, on the other hand, pH increases, and hydroxide ion concentration increases as well. Now that we understand pH, we're ready to take a closer look at the pH scale.